It is a section 14.2, limits and continuity. For limits, let's recall, for y equals f of x, we say that the limit of f of x is L as x approaches a if the left limit and the right limit exists and the same as L. This definition can be redefined by using the epsilon delta argument. For every choice of epsilon positive, there exists a delta positive such that x minus a in modulus is bounded by epsilon, then f of x and L, the distance between these two numbers is bounded by epsilon. We can rewrite this one in this way. That is, x is between a minus delta and a plus delta. Then f of x is between L minus epsilon and L plus epsilon. Okay, let's try to visualize the argument. This is xy coordinates. Then y call f of x. Now we have here a. Okay, so now that it may be at this point it may not be defined. So that's the reason we exclude the case x equal a. But anyway, here that is L. Okay. Once we choose epsilon, then we consider this one. So f of x must be between these two numbers. That means that we may consider here narrow strip. And the function value is inside this strip. And now, for any choice of epsilon, once we choose x inside this interval, in x direction, we can find an interval. Then for every x from this interval, except that point, the function value must be in this strip. No matter how small epsilon is, you can find always such interval in x direction such that if x is chosen from this interval, then the function values must be inside this strip. So in this way, we define the limit. So because always inside this strip, by taking epsilon very small, you can say that the function values and around the point A is now around L. So that is the epsilon delta argument for the definition of a limit. We'll use the definition to define limit for functions of two variables. F is a function of two variables, and domain is D, and now we choose a point AB. Then we say that the limit of f of xy now as xy approaches AB is L, and so we use the notation limit xy approaches AB, f of xy equal L. That is notation if for any choice of epsilon positive, there exists delta positive such that now distance between these 2 points is bounded by L, then the distance between f of x or y and L is bounded by epsilon. Okay, the left figure is for any choice of a point. Here it is a limit. In fact, it is continuous. And right side, and there is a figure of this one. And when xy is 0 and the origin is not defined, and also here the value, once it's approaching through this line, then a value is minus half. If xy is approaching that direction, then the function value is approaching half. So that here, and this is not really satisfied. We cannot choose L. In some direction, the value is half, and in some other direction, the value is minus half, so that we cannot get L. So there is no limit. In fact, it is fluctuating and up and down around the origin. Okay. Now, once you have to find the limit, then sometimes you have to prove the limit exists, or sometimes you have to show that the limit doesn't exist. So when the limit doesn't exist, you may use the following techniques. Here we have a claim. If f of xy is approaching L1 as xy approaches AB along path C1, and f of xy approaches L2 along path C2, then and also if L1 is not the same as L2, then the limit doesn't exist. So if you want to prove that the limit does exist, then try to find two curves such that along the curve the limits are not the same. Then that's the end. So you can find a various paths, but try to find two paths, and along the path the limits are not the same. Then that's the proof for non-existence of the limit. Okay, let's see a problem. Show that the limit of this function doesn't exist at 0, 0. So we may try to choose two paths in this hint, and C1 is when y equals 0. That means that y equals 0 means along the x-axis, now a path is chosen. Then the given problem, given that one, is the same as the same limit, and now y equals 0, so that the function will be x squared over x squared. Now here y is 0. So this one is always 1, so that the limit must be 1. That means along y equals 0 in x direction approach, now the limit L1 is now 1 along the direction. How about x equals 0? That means vertical direction approach. For that one, z equal the given problem. It's the same as now x is 0, so top must be minus y squared, bottom is y squared. This ratio is always minus 1, so that the limit must be minus 1. Along the vertical direction y-axis, the limit L2 is minus 1. Now we found two different limit along two different paths, so that we can say that the limit doesn't exist. Okay. Now, for this one, now we'll try to do the same. Okay, when y equals 0 along the x-axis, the given problem is now top is always 0, limit, and 0, and y equals 0, so the x is 0. This is always 0, so this is 0. Now, how about x equals 0? Then the given problem is the same as limit, and again, the numerator is 0, and denominator must be y squared. This one is again always 0, so this is 0. Now, we chose two paths, but the limits are the same. But the way of approaching to the origin is infinitely many. So you have to do, again, you have to choose another path so that the limit is different from 0. Another choice is x equal y. Now, once x is y, so along the 45-degree angle, now the points are approaching to the origin. Then the given problem is the same as limit, and x is y, so that is 2x squared. Y is the same as x. Okay, now that is 2x squared again. So this is always 1, so that the limit is 1. So in conclusion, we found two paths so that their limits are different, like that, this one and that one. So there's no limit. Okay, how about this one? For this one, does the limit exist? Of course. Now, the point is 1, 1, so that once xy approaches 1, 1, then now the numerator is approaching 2, and denominator also approach 2. So that must be 1. For this one, here the values, this rational function, and also this the bottom is not approached to 0, so that no problem having the limit. But when we deal with this problem, then here once xy 0, 0, then this is a shape of 0 over 0. Okay. Okay. Now, does the limit exist? For this one, now you may start with simply now y equals 0. Then again, you can easily see that given problem, because this numerator will be 0, so that it must be 0, and x is 0, then similarly, again, the given problem has a limit 0. And also, but if you choose, for example, x equal y, as in problem earlier, then the given problem is now here, x equal y, then that is now x cubed, and here that is x squared plus x to the 4. So for that one, again, you have to consider some technique, and so that it may be a little bit complicated. We can decide this one, but anyway, here for this one, now it's not easy. And now for that one, in fact, this one is approaching to 0, but we'll not consider the detail. But here we see another one. So far, for every curve we chose, always the limit is 0. So far, we cannot conclude if the limit doesn't exist. So let's try to choose this curve. X equals y squared. Okay. Now, when we choose this curve, so it's not straight line, and the given problem becomes now limit, and x is y squared. So top will be here y to the 4, x is y squared, x is y squared, so that 2y to the 4. That is always half, so that is a half. So we found two paths, so that along the paths, the limits are different. For example, you can say this one and that one, okay? Now, sometimes you have to prove the existence of a limit. One of the techniques is the squeeze theorem. Squeeze theorem means that f of x, okay, that is between now function g1 and g2. And once g1 and g2 are simultaneously approaching to some value L, then here f must be approaching the same value, because for every x, f of x is always between g1 over x and g2 over x. These two values approach L, then automatically that must be approaching L. That is the main idea of squeeze theorem. We have to use the theorem to show that the limit of this function as xy approaches 0, 0 is 0. First of all, we say f of xy is 3x squared y over x squared plus y squared. Then for this one, we may rewrite in this way, 3y, and then that is x squared over x squared plus y squared. Now, this term is always bounded by 1. So that if we try to measure absolute value of this function, then this portion is now bounded by 1, so that it is bounded by 3y in modulus. Once xy approaches 0, then that will approach 0. So f of xy should approach 0 as xy approaches 0, 0, right? That is a squeeze theorem. Okay, that one, okay, this inequality is the same as, again, f of xy is now bounded by 3y, and here, okay, minus 3y, right? This inequality is the same as that one, and this one approaches 0, then its negation should also approach 0, so that in conclusion, that should approach 0, right? Find the limit for that one. Sometimes the given function has some blocks. Then you may try to consider the block as a variable. As in this hint, we may try to use new variable s as x squared plus y squared. Then the given problem is same as now limit, okay, here there's s and natural logarithm of s. Now, once xy approaches 0, 0, okay, xy approaches 0, 0, then x squared plus y squared must be approaching 0. In fact, these two things are the same. So rather than for that condition, we may write down here x squared plus y squared approaches 0, which is same as s approaches 0. Now from calculus 1, you can finish this one. In calculus 1, to get the value, you did it this way. And there is a logarithm s over, rather than s here, we write down 1 over s. Then as x approaches 0, this goes to infinity, in fact minus infinity, and this is approaching infinity. So that this is form of infinity over infinity. So you may try to use the L'Hopital's rule. So that is same as limit. The derivative of this one is 1 over s, and derivative of this bottom is minus 1 over s squared. And that whole thing is minus s. Okay, that is minus s. So that once you apply limit, then that must be 0. So the limit of this function is 0. Continuity. In calculus 1, you defined this one. A function of a single variable f is continuous at x equals a if limit as x approaches a, f of x equals f of a. This line means these three things. For the left-hand side, the limit on the left side exists. And function is defined at a, and these two values are the same. Once at a point, the given function satisfies that equation, then we say that the function is continuous. Once it is continuous, then it is connected. There's no hole on the graph. We define the continuity of a function of two variables exactly the same way here. If limit as xy approaches ab of f of xy is f of ab, then we say that the function is continuous at the point. If the function is continuous at every point in a region, the domain, then we say that f is continuous on the domain. Okay. F of xy is defined in this way. So that we want to see if it is continuous at 0, 0. What about at 1, 1? Okay. Now, if we want to say that the function is continuous at 0, 0, then this must be satisfied. But earlier, and we show that this one has no limit at 0, 0, around the 0, 0. So this one doesn't exist. So we cannot say that it is continuous. Also, at 0, 0, the function is not defined. Now, once xy, we are choosing xy to be 1, 1, then the function value exists and limit exists, and they are the same. And earlier we solved also the problem so that this one is continuous at 1, 1. This is a rational function. For rational functions, the denominator is non-zero. Then at the point, the function is continuous. Is the following function continuous at 0, 0? What about at elsewhere? Now, for that function, in problem 14.22, we prove that, okay, if we start with this one, then limit and xy approaches 0, 0, and 3x squared y over x squared plus y squared. For that one, by using the squeeze theorem, we prove that the limit is 0. So we already know that for the function g, limit exists. And function value, now, so that one is the same as, in fact, limit g of xy. And xy approaches now 0 and 0. xy approaches 0, 0 means xy is not 0, 0, but become nearer to this point. So once xy is not 0, 0, then it's the same as this one, so that we can write in this way, and we already know that this limit is 0. Now, at 0, 0, the value is defined to be 0. So limit exists, the function is defined, and they are the same. So every condition is satisfied for the definition. So we can say that g of xy is continuous at 0, 0. And of course, for at other points, and this one is continuous. It's a rational function, and denominator is non-zero, so it is continuous. In conclusion, this function, g of xy, is continuous over the whole domain, everywhere. Okay, here we deal with a little bit around computer algebra. When you are solving homework problems, then for some problems you have to use computer algebra. Computer algebra refers to the study and development of algorithms and software for manipulating mathematical expressions. The main thing is to get exact solution. For example, if you are using numeric so the algorithm, then for square root of 2, that must be cut, so that it's not really exact value. But along with the computer algebra algorithm software, you can get square root of 2, that is exact value. There are more than 40 computer algebra systems available over the world, and the popular ones are Maple, Mathematica, MathTalent, and Python. You may choose any of this software. This is MathLab script, and along with that one, I made this figure. Okay, that's the end of section. Thank you.